mic? Okay, excellent. Thank you, Cyril, for a very nice introduction. So hello, everyone, and thanks for joining this session. So I will start my talk by giving you a high-level introduction of our GPU architecture and some programming basics from the CUDA programming model. I will then move on to discuss fundamental performance optimizations that you always need to keep in mind when writing your own CUDA kernels. Finally, I will conclude my talk with some general guidelines and point you to resources for further study. So let's get started. The NVIDIA H200, the most recent GPU based on the Hopper architecture by NVIDIA, is a very complex chip. But the most important thing to keep from this picture is that it has 132 streaming multiprocessors, which are the core processing units of our GPU, coupled with 141 gigabytes of HBM3E at a very high bandwidth of 4.8 terabytes per second. So if we zoom into a streaming multiprocessor, we will see that it is organized into 4 subpartitions, which share an L1 instruction and data cache. Each subpartition has a large register file, as well as multiple arithmetic units for integer and floating point operations, along with our 4th generation tensor cores, which are specialized units for mixed precision, matrix multiply, and accumulate. Now, each subpartition, you can think of it you can think of each subpartition as a SIMT architecture. So what is SIMT? SIMT stands for single instruction, multiple thread. And you can think of it as a combination of SIMD, which is single instruction, multiple data processing, with hardware multithreading. So a SIMT architecture exposes a large set of hardware threads, which it partitions into groups of 32 threads called warps. What it then does is that it interleaves warp execution to hide latencies. And in order to do this efficiently, it needs to keep the execution context of the warps on chip. And this is why we have a large register file. So when a warp actually gets scheduled, each of its threads executes on a given lane of a SIMD functional unit. So what actually happens when threads within a warp actually branch to different execution paths? So in this case, each path is executed separately with its active threads. So as you can see in the example on the right, whenever we have instructions from the blue path executing, there are only 3 active threads, threads 0, 1, and 3. And the rest of the threads are deactivated. And correspondingly, whenever we have instructions from the white path, we have the rest of the threads active and the threads 0, 1, and 3 deactivated. So of course, in order to achieve full efficiency, we want all 32 threads to be converged. So we want them to agree on the execution path. Another important aspect of control flow is actually that each thread in our GPU has its own program counter and call stack. And this means that it is free to execute independently. Okay? So what this means is that you should never assume that threads are converged, even outside of conditional branches. So in the example here on the left, one might assume that after the branch, the threads actually reconverge and execute Z, okay? But there's no guarantee by the hardware that this is actually the case. Okay, so we can have one group of threads from the warp executing Z in one cycle, and then the other threads in another cycle, okay? Of course, the compiler will do its best and try to enforce reconvergence whenever it sees fit, right? But whenever you write your code, you should never make that assumption. Now, the CUDA programming model follows the single program multiple data model of computation. So we basically write scalar code, which is then magically launched on thousands of threads that execute in parallel. And each thread basically uses its thread index to figure out which data to work on or which execution path to follow. So the CUDA programming model, it defines 3 key software abstractions to allow us to program GPUs efficiently. Hierarchy of thread groups, memory spaces, and synchronization. So let's look at the thread hierarchy first. So CUDA defines 3 levels in the thread hierarchy: the grid, the thread block, and the individual thread. So a CUDA kernel is launched on a grid of thread blocks which are completely independent. Then each of these thread blocks gets assigned to some SM, okay, and never migrates from that SM. Each SM may actually have multiple thread blocks running on it concurrently. But we should make no assumption of how thread blocks are assigned to SMs, okay? We have no idea what the order is or if they're actually executing concurrently. Finally, each thread in the thread block actually ends up executing on a scalar CUDA core. So in the Hopper architecture, CUDA actually introduced an optional additional level in the thread hierarchy called thread block clusters. So within thread block clusters, the hardware guarantees that thread blocks are executed concurrently, and they can also exchange data and synchronize efficiently. However, in this talk, I won't be discussing thread block clusters any further, but if you want to attend the next session, you will learn a lot more about thread block clusters. So what about warps? Because we've been talking about warps mostly. So at runtime, a thread block is actually partitioned into warps, groups of 32 threads for SIMT execution. And the way a block is partitioned into warps is always the same. So each warp contains threads that have consecutive thread IDs, and warp 0 always contains the first thread, so thread 0. But what happens actually when the thread block size is not a multiple of the warp size? So in that case, the hardware will basically round up the number of threads, and it will just deactivate some of the threads when executing. So why is this important? Let's look at an example of picking a thread block size. So let's say we want to add 2 vectors of size n equals 1,000, okay? And we are considering 2 options. So option 1 is to define a 1D grid of thread blocks, 10 thread blocks, each of size 100. So we have 10 thread blocks of 100 threads. And then the second option is 8 thread blocks of 128 threads. 128 is a multiple of the warp size, okay? So which option is better in terms of thread resource utilization? Let's take a look. So in the first case, which is on the left, we see that for each thread block, we have 28 deactivated threads. Okay, so this leads to an average thread utilization of around 78%. Okay, but on the left, where the thread block size is actually a multiple of the warp size, we see that only in the last thread block we need to pad by 24 threads. Okay, so in this case we achieve an average thread utilization of around 97%, which is much better, of course. Now let's move on to the memory hierarchy. So CUDA defines per thread registers, right, which give us the lowest possible latency. But we also have per thread local memory. So local memory is used either for statically allocated data in our code, or it could also be used by the compiler to store spilled registers, for example. So this memory is actually backed in the DRAM. That's why it's blue. And of course, because it is backed up in DRAM, it is pretty slow, okay? Then at the thread block level, CUDA defines shared memory. So shared memory is a very fast memory that is visible by all threads in the block. So this memory basically allows us to exchange data among threads in a block. Finally, we have global memory, of course, which is visible by all threads in our grid. And it of course, is the slowest axis in our entire hierarchy. Now, in terms of synchronization, again, we have a hierarchy of barriers, right? So We can synchronize our threads, of course, at the grid level, either when our CUDA kernel finishes, or we can do this explicitly using the cooperative groups API. Of course, this is an operation that is very expensive, so you should avoid this at all costs. Then we can synchronize threads at a thread block boundary. This is the most common way to synchronize threads, and it's very fast because it's hardware accelerated. Finally, we can also synchronize at a warp or subwarp level, which of course is also very fast. Now, in terms of atomic operations, CUDA provides read, modify, write operations for 16 up to 128-bit words. These atomics are available either as CUDA primitives, or you can also use the C++ CUDA library. So we have atomics for shared memory, for global memory, and also for unified memory, which might span our host CPU as well as multiple other GPUs. Now, in order to account for the non-uniform cost of synchronization in our GPU, CUDA actually introduced this notion of thread scopes. So thread scopes, they specify which threads can communicate using a primitive such as a barrier or an atomic. So thread scopes are exposed in 3 ways, either in PTX, which is our virtualizer, in the CUDA math API, or again in C++, in CUDA C++. So the rule of thumb here is to always use the narrowest scope that makes sure your code is correct, okay? And usually the default options are what you need, usually. More on this, again, in the next session on advanced performance optimization in CUDA. So now let's focus on fundamental performance optimizations for our kernels. And let's start with a refresher on Little's law. So let's assume we have an escalator that has 20 steps, and we know that a step arrives every 2 seconds, and it only fits 1 person, okay? So what does this mean? This means that the latency of our escalator is 40 seconds, and the bandwidth of our escalator is 0.5 persons per second. So if I only have 1 person on my elevator, am I actually maximizing bandwidth? So am I fully taking advantage of my escalator? And the answer is no, because with 1 person in flight, I achieve a throughput of 1 divided by 40 seconds, which is 0.025 persons per second. So what if I actually want to saturate my escalator? What do I need to do? This is basically what Amdahl's law, what Little's law tells you. So Little's law tells you that the level of concurrency you need to saturate your device, escalator in this case, is given by the bandwidth times the latency. So in this particular case, we need 20 persons in flight to actually saturate our escalator. So how is this relevant to GPUs? So Little's law can help us understand how to maximize performance for GPUs as well, right? So on GPUs, we typically need to hide either compute or memory latencies. And latencies, Little's law tells us that in order to hide them, we basically need to have enough concurrency. And by concurrency in this case, we mean instructions in flight, okay? So let's say we have 8 FP32 units, okay, with a latency of 24 cycles, okay? And let's assume that we can actually issue 8 operations per cycle. So in order to saturate these units, what level of concurrency do I need? I need to multiply the bandwidth, right, with the latency. So if I multiply 8 by 24, I will get the level of concurrency I need, the level of in-flight instructions I need to actually saturate this device. So how do we actually increase in-flight instructions on our GPU? There are 2 main ways to do this. One is to increase instruction level parallelism. So having more independent threads, more independent instructions per thread can help. And the other way is to increase thread level parallelism. So basically spawn more threads, because if you have more threads, you have more instruction streams, which means more, again, independent instructions in your kernel. So let's focus first on an example of how increasing ILP can help our code. So here we have a very simple kernel that where each thread basically updates one element, okay, in vector C. So if we compile this code and look at the assembly, we will identify that it basically consists of 3 loads for the values of A, B, and C, a fuse multiply add operation, which does the arithmetic, and then there is a store for the result, okay? And if we actually execute this on our hypothetical machine here, it will take like around 1,000 cycles to complete. Now let's say we increase ILP in this kernel by computing more elements per thread. Okay, so we are trying to compute 2 elements per thread in this particular case. And the way we do it is by actually looping over a grid stride. Okay, so if we actually compile this code and see what it looks like, we will see that actually not all of the loads seem to be independent. It seems that something is making the compiler think that it cannot parallelize all of the loads and all of the stores. So what's going on here is that the compiler, because we are using a grid stride loop, which is a value that is unknown to the compiler, it cannot figure out that our 2 indices, I1 and I2, are independent. So in order to be on the safe side, our compiler cannot completely parallelize, let's say, these operations. So what we end up having in this case is approximately twice the number of cycles for twice the amount of work. So basically, we didn't gain much here, okay? So in order to achieve what we actually want, we need to use a constant block stride, okay? Because this actually allows the compiler to generate efficient code. So here you can see that all of the loads are done before the arithmetic operations, right? And they are independent loads. So this means that we can have more instructions in flight, more bytes in flight in this particular case. Then we have the 2 FMA operations and then the 2 stores. And if you actually run this on our imaginary machine, we will see that in the same number of cycles that we did 1 element, we actually do 2 elements now, okay? So now let's switch to warp scheduling and trying to understand how actually having more active warps per SM also helps our code. So on Hopper, we have 4 warp schedulers per SM, 1 per each subpartition, and each warp scheduler manages 16 warps. So it has 16 warp slots. And it can issue 1 warp per cycle. So let's assume we have 3 possible states for our warps. The first state is the stalled state, which means that our warp is waiting for something. It's waiting for an instruction fetch, a memory dependency, execution dependency, synchronization barrier, whatever. Then we have the eligible state, which means that it's ready to issue a new instruction. And the selected state, which means that the scheduler selected it for execution. Okay? And let's assume here we only have 3 active warps in our warp scheduler. So we have 2 that are stalled and 1 that is eligible. So what will happen in this cycle is that because we have an eligible warp, the scheduler will select that warp for execution. So that's fine. Everything is perfect. In the next cycle, however, all of the warps are stalled. Okay, so in this cycle, basically we have nothing new to schedule for execution. So this issue slot is unused. Then let's assume that the warp number 0 is eligible again. Okay, so in that cycle, the warp scheduler figures it out, selects the warp for execution, so everything is good again. But now let's assume that all of the threads are stalled, and then they start to exit. So the main thing I want you to keep from this picture is that if we had more active warp slots in the first place, it would be easier for us to hide these empty issue slots and actually use them. okay? So, So how can we actually increase the active warps per SM? So there is a maximum number of active warps that can be concurrently active on an SM. Okay, so we have the device maximum, which depends on the compute capability of our GPU. And then we have the achievable maximum, which depends on our CUDA kernel, on the implementation and the compiler, basically. And then we have the actually achieved number of active warps, which depends on the grid we actually use to run our code, to launch our kernel. So we define occupancy as the ratio of the achievable number of active warps per SM to the device maximum number of active warps per SM. Okay, and occupancy in a CUDA kernel can be limited by multiple factors. So one is register usage, another is shared memory usage, and another is thread block sizing. Okay, so whenever you need to tune occupancy for your code, you would actually use a tool such as Insight Compute to see what your occupancy is and what you need to do to tweak it. But here I will just go through a couple of examples just to give you an idea of how it works. So let's assume we have a kernel that uses 63 registers per thread. Okay, so this means that we have around 2016 registers per warp, but registers are allocated in fixed chunks of 256. So this number is actually rounded up to 248. Okay, so we know that for this particular GPU we're looking at, the Hopper GPU, we have 64K registers per SM. Okay, so how many active warps can we have based on this register file size? We just divide 64K by 2K and we get 32 warps, okay? The theoretical maximum though for Hopper is 64. So for this particular kernel, we can only achieve 50% occupancy. Similarly, we can see an example here where shared memory is a limiter. I will not go through it in detail. And then finally, thread block sizing can also affect occupancy. So just quickly here, we can see that for a thread block size of 32 or for a thread block size of 768, you can actually only get 50% occupancy for your kernel. So let's go back to our simple vector update kernel and see how ILP and TLP can affect its performance. So in our first experiment, we take our baseline code where we only computed one element per thread, and we increase occupancy. Okay, so we go from 50% occupancy to 100% occupancy. And we see here, by comparing the first two lines, that performance basically doubles. So when we go from 50% to 100% occupancy, we get half of the execution time. Okay? Then in our second experiment, we will work with ILP. So we will increase the number of elements per thread to 2 and 4. And in this case, we see again that by going from 1 to 2 ILP, we have a 2x boost in performance. And then by going to 4, we again have a performance boost, okay? So obviously, both ILP and TLP are different ways of hiding latency on our GPUs. So the question here might be, what occupancy do I actually need for my kernel? Should I always aim for 100%? So the rule of thumb here is that you should always try to maximize occupancy. However, not all algorithms are as simple as the vector update example I showed earlier, right? So there are kernels that need to use a lot of registers, okay? Or there are kernels that have a lot of data reuse and would benefit from having your data in registers to enable fast access, okay? So GEM, for example, if you look at like highly optimized GEM kernels, they have high reuse, and they actually run at low occupancy for that reason, okay? Because it's better to go to registers for faster access. So let's switch our focus now to the memory hierarchy and how we can actually maximize memory throughput on our GPU. So let's go quickly again through the hierarchy. We have our large register file, our unified shared memory / L1 cache. We'll talk about that later. We also have an L2 cache and our DRAM memory. So someone might ask, why do GPUs even have caches in the first place, right? Because if you think about it, you have thousands of threads sharing the L1 and hundreds of thousands of threads sharing the L2. So you end up having a couple of bytes maybe per thread, right? So caches on GPU are useful mostly for smoothing irregular access patterns. They are useful for caching data that is accessed by multiple threads, right? They allow us to also get a faster access to local memory. And also, they help us get faster atomics, okay? So somebody coming from the CPU optimization space might ask, what about cache blocking? Is it relevant here? So the first answer is no, that it's difficult to use cache blocking in a GPU, but it's not impossible. So again, in Igor's next session, there will be an example where L2 cache blocking is useful on a GPU. So in terms of data movement and memory transactions, in general, the minimum memory access granularity on a GPU is what we call a sector, which is equal to 32 bytes. Okay, so when we move, for example, data from the L1 to the L2, we move one sector. When we move data from the L2 to global, by default, we move two sectors. But that is something actually that can be tweaked. Now, the cache line size is actually 4 sectors, okay, 128 bytes. Now, when we do a global read, what happens, of course, is that first we check in the L1. If the data is not in the L1, we check on the L2, and so on and so forth. And the unit of data that is always moved is a full sector. Okay? Now, for writes, it is good to know that the L1 is a write-through cache, which means it updates both the L1 and the L2. And the L2 is actually a write-back cache, so it only flashes to DRAM in case of evictions. So for writes, the hardware actually has the capability to move partial sectors, but for GPU, for a data center level GPUs at least, where ECC is enabled, error correction code, due to ECC, basically a read is transformed to a read modified write operation. So because you need to fetch the data to do the error correction code, so you end up moving a full sector again. So just keep in mind that moving full sectors is optimal. Now let's look at some global memory access patterns and see what is efficient and not. Okay, so this is like the best possible scenario where threads in a warp access data that is aligned and sequential. Okay, so this is a perfect scenario where we end up fetching exactly the number of sectors we need, okay, which is 4 in this case. Now, in this scenario, each warp is accessing 8 bytes instead of 4 in the previous example. But again, like the addresses are aligned, okay, and sequential. So this again is the perfect scenario, right? Nothing changes here. It will just take like more cycles to fetch the data, right? Because we're fetching 8 sectors instead of 4. Now this pattern is similar. It's aligned. The only difference is that it's non-sequential, but it doesn't matter because the only thing that matters is the number of sectors we need to move. Okay. So again, here we only move 4 sectors, so this is perfect. Now let's see what happens if our memory is actually misaligned. So in this case, it's misaligned and sequential, and here we actually need to fetch 1 extra sector, okay? So instead of 4, we fetch 5. So this is not that bad when we have other warps, right, that are going to reuse the extra sector we brought in. So in this case, for example, we have another warp in the same thread block, let's say, that is accessing the next sectors. So in that case, the effect of this misalignment is not that significant, okay? So here we have a same address pattern. So in this case, since the minimum we always move is one sector, here we actually just move one sector, okay? So we are wasting some bandwidth, but it's still okay. Now the worst possible scenario is when each thread touches a different sector. So here, for example, we have an aligned axis, but it is strided. And basically every thread in our warp touches a different sector. So this is the worst possible scenario. And this is something you should strive to avoid in your code. Now let's look at an example of comparing array of structures versus structure of arrays. So let's assume we have a struct of coefficients that has the memory layout you see here depicted. And let's say we want to access the U data member and Y of 0. So what happens in this case? So when we access U, basically, we access 4 bytes of data per thread at a stride of 80 bytes, okay? So this is the worst case scenario we described earlier, okay? Each thread in our warp is accessing a different sector, okay? So here we are accessing U, and then we are accessing Y of 0, okay? And in this particular case, we are not even reusing the extra data we brought in when we brought in U, okay? So this is awful. We are actually transferring seven times more bytes than we should be, okay? But if we switch to a structure of arrays approach, we solve our problems. So if you can actually, if your application allows it, like structure of arrays is usually more efficient for the GPU. So as you can see here, if we switch to structure of arrays, in the first access to U, we basically have the perfect scenario. Okay, threads in a warp, access contiguous aligned data. Okay, and it's the same for Y. And just to give you an idea of what the performance impact is here, I am actually comparing the two implementations, and you see that there is around almost a 6x performance boost by switching from array of structures to structure of arrays. Now let's move on to the unified L1 and shared memory, okay? So this memory, it's called unified L1 and shared memory because it can actually be used either as a hardware managed cache, that's when we call it L1, or a scratch pad, basically a software managed cache, in which case we call it shared memory. And you can actually pick a carve out. So you can say, I want like one part to be used as L1 and another as shared memory. You can do what you like. So shared memory can be useful, right, to store frequently accessed data in our thread block. It can be used again to improve global memory access patterns. And most importantly, it can be used to exchange data between threads in our thread block. So in terms of how this memory is organized. So first of all, it's by default, we have 48 kilobytes per thread block, but we can actually opt in to use more. So we can opt in to use, for example, 227 kilobytes on Hopper, okay? So this memory is organized into 32 banks, and each bank is 4 bytes wide. So, and successive 4-byte words are mapped to successive banks. So this is a very fast memory. Of course, it's not as fast as registers, but it's a lot faster than global memory. So just to give you an idea of how data would be mapped to the banks, here we have 4-byte data, okay? And basically every row here, every column, sorry, is mapped to the same bank. So here, elements at address 0, 128, 256, they are all mapped to bank 0. And the next ones are all mapped to bank 1, and so on and so forth. But what actually happens when I access 8 bytes data or 16 bytes data? So in that case, it just takes multiple phases to process our data. So for example, if we have 8-byte data, we basically need 2 phases to fetch our data. okay? And if we have 16 bytes, we need 4 phases. So if we look again at access patterns, in shared memory though in this case, what is important to remember is that the perfect scenario is, of course, when threads in our warp access different banks, okay? Because that's how we get parallelism, through banks. So in this scenario, which we call coalesced on the left, each thread is accessing 4 bytes data contiguously, okay? So this is, again, the perfect scenario. The middle case is the worst case scenario, because here we actually have what we call bank conflicts. Okay, so here every thread is actually writing data to shared memory with a stride, okay, a stride of 2. So in this case, we end up having half of the warps in the thread competing with the other half of the threads in the warp to access the same banks in shared memory, okay? So this is a 2-way bank conflict, but it could be a lot worse. It could be like a 32-way bank conflict. And then another scenario, which is fine, is the broadcast case, okay? Where basically all of the threads in the warp are accessing the same address. So that is also fine. Now, let's look at an example where we actually have bank conflicts and what we can do to resolve them. So let's assume we have a 32 by 32 array of floats in shared memory, 4 byte data. So we basically end up having 1 element per bank, okay? We have a row major layout, and let's assume here let's just focus on 1 thread, okay? On 1 warp. So we have each warp. Let's say we want each warp to access a column, okay, of this shared memory array. So if each thread, if each warp accesses a column, what ends up happening is that we get a 32-way bank conflict, okay? Because in this case, a column is mapped to a single bank of shared memory, so there is no parallelism. The accesses are serialized. So what we can do to fix our problem is to pad our array, okay? So here, instead of having a 32 by 32 array, if we pad 1 dimension, we basically change how the data is mapped to banks. And we end up with something that looks like this, okay? And this resolves our problem, This resolves our problem because we end up having threads in a warp, which are accessing a column, working on different banks. Now, another solution, which doesn't waste shared memory, right, because we don't need to pad, is to actually change the way we index the data. So we can do something which is called swizzling. So if we do this, we get the same effect, but without wasting shared memory. Now, let's move on vectorized memory accesses. So if we have a single warp accessing 4 byte data, okay, for ints in this particular case, then 1 single warp ends up fetching an entire cache line in this case. However, if we use the vector data types that are available in CUDA, we can, with int2 in this particular case, with 1 single instruction, actually fetch 2 cache lines. And if we use int4, we can, with a single fetch, bring in 4 cache lines. So vectorized memory access is available for both global accesses and shared memory accesses, but it requires aligned data. Okay, so this is something the programmer needs to guarantee from his side. And it works on either 64 or 128-bit data. So vectorization is important because we execute less instructions, which is always good, okay? And it actually allows us to have more bytes in flight, which is what we want, again, based on Little's law. So there are 2 ways to do vectorization. One is by using the vector types explicitly that are available in CUDA. So in this example, instead of floats, we use float2s, and the compiler does the work for us, basically. And then the other way is to cast our pointers, okay? Now, again, if we look at an example, at the previous example, our baseline code, which is using floats, achieves memory bandwidth utilization of 60%. But if we actually use float 2 and float 4, that increases to 84 and 88% utilization, which is pretty good. So overall, in terms of global memory, you need to always remember that ideally you need to have aligned and coalesced accesses within a warp always, okay? And the other thing is that always try to maximize the number of bytes in flight, because that will allow you to saturate memory bandwidth. And you can do this either by processing multiple elements per thread, or using vectorized load stores, or increasing thread level parallelism, basically. Then the L1 and L2 caches, as I said earlier, cache blocking is difficult to do, but not impossible. And the general rule is to rely on the caches when you don't have a choice, okay? So ideally, you want to be using shared memory whenever you have data reuse in your code. But in this case, of course, you need to make sure to avoid bank conflicts. So let's switch now to the final topic, which is atomics, which are also important for some codes. So let's look at 3 different patterns. So for, let's say we have same address atomic. So we have every thread in our warp doing an atomic operation on the same address. So this is the worst possible scenario because all of these operations are serialized, of course, okay? Then in the middle case, which we call scattered, basically we have, it's random access basically. So we have each thread doing an atomic operation on a different cache line, okay? So this is quite performant, okay? But the best possible scenario is again what we call coalesced, where most of the atomics within a warp are coalesced, so are basically on contiguous data, okay? So let's look at an example, okay? So where we start with a naive implementation that uses atomics and try to improve it. So here, we basically just want to compute the maximum value of an array, okay? In our initial implementation, what does it do? It uses a grid stride loop and first computes a local maximum, right? And then each thread does a global atomic, right, to update the global maximum, okay? So one way to improve on this would be to maintain a local maximum per thread block, okay? Because that would then reduce the number of global atomics we do. So to be more specific, we maintain a block level max in shared memory. And then what we do is each thread, again, computes its local maximum. Then it atomically updates the block level maximum, which is in shared memory in this case. And then only one thread from the block, one representative thread, actually updates the global max, okay? So here we've basically replaced a lot of global atomics with shared memory atomics. The other thing we can do is actually use a parallel reduction to compute the block level maximum, okay? And a very useful tool to do that in CUDA is to use cooperative groups. So with cooperative groups, you can define a tile. In this case, we define a tile of 32 threads. And then what we do is we do a block level reduction. Not important how this is implemented at the moment. You can ignore it for now. So we do a block level reduction of the max. At the final level, we do a warp level reduction because that is very efficient actually on GPUs. And then again, only one thread in the thread block does a global atomic, okay? So if we actually compare the performance of these 3 implementations, we see that shared memory atomics gives a huge boost. And then the shared memory reduction also gives an additional boost. So another example, which is a bit unconventional, is unconventional because it's not using atomics in the first place. Okay, so let's say, again, we have a vector update. Okay, so we have each thread doing a grid stride loop and updating an output element in a vector, okay? So what happens here is that we basically have 3 reads in our loop and 1 write, okay? What we can do instead is replace this vector update, okay, with an atomic add operation. And why would we do that? Why the hell would we ever do that? So the thing is that atomic operations in global memory are actually offloaded in the L2 cache, okay? So we implement something that is kind of like fire and forget. So basically, what happens is we don't actually read A anymore in registers. So we read only B and C, right? We do the add operation, the multiply operation, and then the update of A is actually done in the L2 cache. So basically, the value of A is never fetched in registers, okay? So that reduces data movement a lot in our memory hierarchy. And what this allows is basically, it reduces the latency of the vector update, okay? And this allows us to have more instructions in flight, which means more bytes in flight in this case. So if we actually look at the output of n-site compute for this particular kernel, and we look at the transfer sizes in the memory hierarchy, what I have circled there basically shows that we don't read vector A, right? So it shows us basically that we are reducing the data movement between the SM and the L2 by 33%, okay? And the other important thing is that we actually improve global memory bandwidth, which is basically what I told you earlier. So because we reduced the latency of the operation, that allowed us to get more instructions in flight, which translates into more bytes in flight. And more bytes in flight means I can better saturate my memory bandwidth. So in this particular case, we increase memory bandwidth by around 4.8%, and this directly translates into an improvement in execution time, okay? And this is the case because actually this kernel is a memory bandwidth bound kernel. Excellent. So let me just give you some general guidelines of what to do depending on what the characteristics of your code are. So if your code is compute bound, okay, usually what you need to do is to reduce your instruction count by using, for example, vector load stores. Or you can use our amazing tensor cores if, of course, your application can be somehow transformed into gems, right? Or if, again, your application can tolerate a lower precision, then you can use lower precision arithmetic and fast math intrinsics, okay? Now, if your application is bandwidth bound, this means that you always want to try to reduce the amount of data that is transferred throughout the memory hierarchy. So, of course, you need to optimize the memory access patterns based on what we discussed earlier. Again, you might want to use lower precision data types because that also saves bandwidth. And you can also try and do kernel fusion because that saves also round trips to global memory. Finally, if your code is latency bound, then basically you need to do what Little's law tells you and try to increase the number of instructions and memory accesses in flight, okay? And ideally, you want to do that either by increasing parallelism, instruction level parallelism, occupancy, or both, okay? So that concludes my talk. Here I have some useful links. So the CUDA best practices guide is always a good read. Our CUDA samples are excellent. And of course, there are multiple GTC sessions in the performance optimization track. The advanced performance optimization in CUDA is actually the next talk. And I believe the rest are on Wednesday. So thank you very much. And I'm happy to accept questions now, if there are any. Yes?
So I have a question. When you are writing an application for general purpose GPU programming, you don't sometimes know which hardware you're going to be running on and which architecture is going to be, is going to be running your application. So some of the optimization is very tied to the knowing the numbers of the particular, whether this is Hopper or something else. Is there a general advice on writing something that can run on a, you install the software and it can run on the customer's laptop and you don't know what they have other than the fact that they will have an NVIDIA GPU?
Right, so in this particular presentation, we didn't actually do anything that is Hopper specific. So the next talk will have some specific Hopper specific features, but in this particular talk, if you just follow these optimization guidelines in every single kernel, they will be future-proof in a sense.
I was talking about features. I was talking about, picking to achieve maximum utilization, picking the number of blocks, picking the number of threads, like all of those things. That depends on which architecture you're using, isn't it?
Yes, usually it does, right? But like the idea there is just to follow the general guidelines, and then if for one particular architecture you need to squeeze out every possible inch of performance, then you will try and take the extra step, right? That's how I would approach it. I would just follow the general optimization guidelines, and then if I'm interested in one particular architecture, right, I would just focus on that then.
Yep.
Yes.
Next question.
Is there a reason, here in the middle, is there a reason you did not mention textures or surfaces?
Yes, I didn't have enough time to cover this topic, right? There are a lot of things to talk about.
Okay,
Yeah.
thank you.
No worries.
Hi. I noticed early in your presentation that you mentioned that thread blocks are locked to each SM. You can't migrate.
Sorry, can you speak louder?
That early in the presentation,
Yes.
you mentioned that thread blocks are sort of locked to an individual SM and you can't have them migrate between
But they do
SMs.
not migrate, no.
Was there not a recent architecture change that made it so that certain SMs can share thread blocks, or?
No, not that I am aware of, no.
Ah, okay, thanks.
No worries, thank you. Yes.
If you have any question, can you go to the mic, please? Thank you. So everyone can hear the question. If you don't mind.
So how would you approach the optimization of CUDA code that was written for GPUs about like 10 years ago for like pre-Kepler era and get that code to run fast on today's GPUs?
Okay, well, I would, first of all, just make sure that they follow all of these optimization guidelines, right? And if they do, then they will pretty much be running, be in a good state, right? They might not be running at speed of light, but they will be close to speed of light if they're just following these guidelines. And then if, for example, I would do something Hopper specific, maybe just because it has a lot more SMs than older GPUs, I might focus more on increasing the level of parallelism in my application, okay, something like that. But first step is to make sure that all of these performance guidelines are applied, and then in more recent GPUs where we have more SMs, maybe increase parallelism in your code.
So you showed a profile of the memory utilization, memory bandwidth utilization, and so
Yes.
my question is, what are the different ways which are? I mean, I have to profile the memory bandwidth utilization of applications, right? So you showed one such. Are there others?
Are there other what, metrics or?
No, other ways to profile the memory bandwidth utilization.
So I actually used NCU, right, to do all of this work. So that is like the tool of choice, right, for NVIDIA GPUs. You just use NCU because it gives you all of the metrics you need to look at. Did that answer your question?
So let's say, so NCU doesn't work in certain scenarios, right? If there is a communication kernel that I'm trying to write using CUDA, so in those cases, anyway, I can ask you later.
So NCU, it profiles at a kernel level. So it profiles individual kernels. So you should be fine if you're just focusing on an individual kernel. Is that what you're asking?
Yeah, but if I have a sequence of operations of multiple kernels that I want to measure the memory
Then you
bandwidth.
should look maybe at Nsight systems, right, which gives you the whole timeline. And then depending on what you see on your timeline, like what looks like the biggest bottleneck, then you just focus on that particular kernel and look at it through NCU.
Cool, thank you.
Yeah, no worries.
Hi, I'm just wondering because sometimes I'm writing a few kernels in .ptx format.
You use PTX?
Yes.
Amazing.
And what I've been noticing after I compile it into the .cuban and I actually read it out using the Q object dump afterwards, there have been modifications that you guys create after the fact, even though it's still in PTX format.
Well,
so
PTX is a virtual ISA, right? So,
but there's like additional instructions that get injected in every now and then. Are there any rules that we should be aware of that we should be following if we're working with .ptx format?
sorry, can you go closer a bit to the mic? So what was the question?
So sometimes there's additional instructions that were getting injected into the .ptx.
Yes, which I assume depend on the compute capability, right? You're compiling for. It
no,
might change.
No, it's like one of the examples was return function, so it just added an additional function that had a thing called ret, so it just calls it. It looks like it's absolutely useless for any.
Okay. Well, I'm not. I think that's more of a question for the compiler team. Actually, I'm not sure what to answer here. Is the question like why the compiler is adding more instructions than you were expecting?
It's more so. Is there any documentation on identifying where these additional instructions would be added into it?
I believe not. Right? Because.
Thank you.
Hello. Thank you for the talk. For our kernel, we are thinking that we need to be using more register space. And I'm curious if we
were running at lower occupancy?
Yeah, exactly.
Okay.
And so we were thinking, would we be able to get, say, twice the amount of register space per thread if we were to have the number of threads? Or does it not work like that?
No, there's a limit, right? There's a limit of 255, 256 threads, registers per thread anyway, right? Oh, okay. So you need to always keep that in mind. And you always need to keep in mind that if you don't have enough registers in your register file, you need to be careful because the compiler will do what we call register spilling and use local memory, right, for the extra registers. So you always need to pay attention at what the compiler is actually generating, okay? To optimize your code. There's usually a sweet spot.
Okay, is the best way to know through like Nsight Compute or just to profile it and see when it gets
Nsight Compute helps, right? Because there's an occupancy calculator and it also shows a register usage, right? And like how changes in register usage can affect your kernel. So it does help.
Okay, thank you.
Are those slides available somewhere?
Yes, they will be available, I think, in 72 hours, something like that.
And one question about the load-to-load data dependency in one of the earlier slides. Did I read that
in the ILP example?
Yeah, in the very first, one of the first few examples, you showed two loads can be executed consecutively one after the other.
Is that let me go to what I think you're talking about.
Yeah, I think that was the ILP slide.
Was it the first example? Was it this one?
Yeah, I think this one.
Where I was explaining why the compiler does not do exactly what we want?
Yes.
Okay, yes.
I just wanted to make sure that there was a load-to-load data dependency.
So the problem here is because it doesn't know that I2 and I1 overlap, okay? It can't load like the I2 index of the C vector, right? Because it could be equal to C1, So in that case, it needs to do the FMA and the store of C1 first, and then load C2, because it could be the same.
I see.
Yeah.
Because of the restrict keyword up there?
Sorry?
Because of the restrict keyword up there?
No, the reason is that the grid stride here is not fixed. It's not a compile time constant. So the compiler cannot know that the grid stride here is not 0, for example, okay?
I see, it's the same.
So in the next example, we're basically just using a constant block stride, and that solves the problem.
Okay, thank you.
Yeah.
So how do I know the size of the shared memory it's available to me?
The size of the
Shared memory.
shared memory? You can see that in compute or like in the white paper of each, in the documentation. We have documentation that says per compute capability what is available.
Okay,
right,
so
but you can also see it in NCU when you
there's
profile.
Is there a query in the API to say?
Is there a what?
Query, we just ask for it, there's an API that I can just ask for it. So how much of it?
In the CUDA API?
Yeah.
Yes, there is. There is.
There is one? Okay.
Yeah.
The other question is, what's from a CUDA point of view, what's the future for the persistent kernel? Is that going to be banned sometime, or is not allowed?
I don't think I have the expertise to talk about persistent kernels because I haven't written ones myself. But I do believe they are still used heavily, right?
It will be around for a while, or is it going to be disallowed down the road? I'm just curious.
I don't know. I don't know if somebody else can answer.
Yeah, persistent kernels. For sure. Okay, well, thank you.
All right. If there aren't any more questions, thank you all very much for attending. Thank you.